Hi everyone. So this lecture, we're going to be talking about linear kinetics of human movement. We'll be looking a little bit at kind of a change in momentum. Once again, we'll be looking at potential and kinetic energy. We'll be looking at what elastic and plastic movements are, or elastic and plastic properties of movement and objects. Like once again, the intro to kinetics, um, the angular kinetics, and a little bit of our kind of when we talk about equilibrium are going to be a large part of the upcoming exam. So I hope you guys, if you have any questions, please get a hold of me, and I'll be more than happy to help you with the understanding of them. So in this lecture, we'll talk about linear kinetics. We'll also talk about the three laws of motion, but kind of we'll be looking a little bit how you can improve traction on an icy surface. Why do some balls bounce higher than others? They're more elastic. And how can a football lineman push larger opponents backwards? We use linear kinetics to kind of answer these types of questions. So let's first look at the three laws of motion. These were developed by Isaac Newton long time ago, around the time he was developing the study of calculus, before age 30, once again. So we have our first law, a law of inertia, which basically, once again, means it's basically if a body will maintain a state of rest or constant velocity unless acted upon an external force that changes that state. Remember, motion doesn't just occur. A sum of motion or a sum of forces needs to, or a net sum of forces needs to be present. This seems intuitive that a stationary object will remain stationary unless acted upon by external forces, but what about objects in motion? Well, we still need a net force to determine that. We can look at friction, air resistance. These are external forces that act to decelerate a body in motion. Or if we're looking at sails on a sailboat, if they are rotated in a certain direction, air resistance will change its direction vector, and we'll see a change in the direction of motion. So we're still seeing kind of that law of inertia acting upon that. We're still changing its state of motion because, once again, remember, forces are vectors. They have magnitude and direction. So let's look at Newton's second law of motion, which is the law of acceleration. An applied force causes an acceleration of the body with a magnitude proportional to the force in the same direction of the force, and it is inversely proportional to the object's mass. So force equals mass times acceleration, okay? Remember, mass is in kilograms, acceleration is in meters per second squared, okay? Or like this too, okay? So let's look at each component of this law. If we increase force and acceleration, we can keep force and acceleration the same, or we can increase mass and decrease acceleration. Usually, if we increase force and increase acceleration, we're going to increase velocity. If we keep both of these exactly the same, there'll be no change in velocity. And if we increase mass and decrease acceleration, we're most likely to see a decrease in velocity. Okay? I hope that makes sense. So let's look at some more examples here. We have a 2-kilogram ball struck, let's say by a bat, with a force of 10 newtons. So what would be the acceleration? Well, acceleration is force equals mass times acceleration. So if we know that, if force equals mass times acceleration, and we're trying to calculate for acceleration, we simply divide both sides by mass. So acceleration is going to equal force divided by mass. So we have our force here is 10 newtons divided by 2 kilograms. So we're going to have an acceleration of 5 meters per second squared. We can do the same thing here. 20 divided by 2 is going to give us 10 meters per second squared. And then finally, 1 kilogram ball struck with a force of 10 newtons. Once again, 10 divided by 1, we shouldn't have to write that down. It's going to give us 10 meters per second squared. Okay, so when we change this stuff, it's important to do the math. If you throw a heavy ball versus a lighter ball, which one has more acceleration? Generally, it should be the heavier ball, but it depends on how much force you're using. If you throw with more force, will the ball have more or less acceleration? Depends on the mass of that ball. So these are all important, okay? So let's talk about Newton's third law, the law of reaction. For every action, there's an equal and an opposite reaction, okay? This is the reason when you're standing on the ground, you don't fall towards the center of the earth and bounce around for a bit, is because if you're standing on the ground, you're applying your weight. Remember, weight equals mass times gravity, and gravity is equal to 9.81 meters per second squared. So you are applying this force to the ground pushes back against you, hence you don't fall through the center of the earth. Let's look at two hockey players. We have a 130 kilogram hockey player and it collides with an 80 kilogram player. If the first player exerts a force of 450 newtons on the second player, how much force is exerted by the second player on the first? Well, according to this third law of motion, the law of reaction, we're going to see that the second player will exert 450 newtons of force on the first player because it's going to be equal and opposite. This leads us to our ground reaction forces. Once again, when we're standing, gravity accelerates the body towards the ground. Without an equal and opposite ground reaction force, the object would be driven into the ground. Okay, essentially, we just translate through the ground, nothing would happen. But because the ground reaction force is pushing against us with an equal and opposite force, we stand. When we're looking at gait, when a person's walking, when the foot contacts the ground after the swing phase, the ground generates an upward reaction force. So our foot then complies by going upwards, and then if we're pushing against the ground like this, draw it again, push against the ground like this, the ground will then push against us like that. So we go forward and up and to the right. So let's look at kind of our force time curves for each activity. When we're standing, okay, it's basically the same. We have our body weight, but we're not applying any additional force to the ground. So we have an equal and opposite force. It's simply our body weight, okay? If somebody weighs 100 kilograms, let's say their mass equals 100 kilograms, okay? And we have, acceleration due to gravity is 9.81. 100 times 9.81, it would give us 981 newtons. So we'd simply say that our body weight of 981 newtons is being applied to the ground, so that the ground is applying 981 newtons to us. Same thing with the anterior-posterior directions, or f of x. Because we're not pushing against the ground, we're not pushing in the x direction, it would actually be 0, okay? But if we're looking at gait, once again, we're stepping on the ground, okay? We have our heel contact, so this is our body weight. Because our legs have a certain amount of velocity, then because they have weight, they're gonna have some force against the ground. It's gonna be higher than our body weight against the ground, and then we'll have this kind of negative dip right here as we kind of go into our mid stance. Okay, we're simply complying with the ground there. And then we go to toe off. We're pushing, we're using our muscles to extend our legs, so therefore our foot is pushing against the ground. So for us to move upwards and forwards, okay, we're applying a greater amount of force than gravity or our weight. So it's going to be greater than our body weight, so we can move forward. In this case, we're moving upwards. If we're looking at the anterior posterior forces, or F of X, we see the same thing. It's a little bit more broader, but we see essentially the same. We are just standing there. There's nothing. As soon as we apply, or as soon as our heels strike the ground, okay, it's going to be negative. So once again, if we're pushing our heel contacts the ground like this, the ground is going to push backwards on us. So we're going to see negative here. But then we're doing our toe off. So then our foot is applying force to the ground like this. So the ground is going to push back like this. So we're going to see positive right here. This is also why if you've studied like running mechanics, you're watching somebody run or you've looked into this, this is why when you're running, you shouldn't really do heel striking when you're running. You shouldn't really land on your heels while you're running. Besides the fact you're placing at full leg extension, all that force is going to be directed through your heel all the way up into your leg, into your hips, and like that. So it's not super great for your joints and bones. But also is if you're running and you land on your heel, it's also just inefficient, because if you're landing on your heel, you're pushing down against the ground like this. So the ground is going to push you backwards. That's the exact opposite of what you want to do when you are running. But if you're running, if you're trying to run correctly, like as far as being fast and efficient, you're pushing yourself backwards. You're actively braking when you should be moving forward. If you're landing on your forefoot, you're doing an example like this. So you're pushing against the ground so it propels you forward without that braking movement. Hope that makes sense. So we're going to see downward deceleration and then acceleration upwards. So the ground reaction forces represent the summation of the acceleration of all the body segments. Muscle contractions and or any other sort of extra external forces can accelerate or decelerate the individual segments. Segment acceleration are influences of the ground reaction force. In this manner, the ground reaction force is both reflect the movement of all body segments and reflect the movement of the entire body center of mass. Okay, in order to perform skilled movement, the person must learn to manipulate the ground reaction forces. Really, the way we do this is through muscle activation to produce the ideal movement. This is a lot like when we were talking about running. Is if you're running, you want to manipulate your muscle activations so that you land on your forefoot like this, so that the ground reaction force will comply and push you forwards and upwards. If you are landing on your heel once again, you're going to have a vector like this. So the ground reaction force is actually propelling you upwards and backwards instead. And also just a continual application of a lot of force to your heels directed all the way up to your leg and to your hips is not necessarily ideal for your muscles and joints, or your bones and joints. So let's look a little bit more into the mechanical behaviors of bodies in contact. Okay, especially when we're going to lead into kind of friction and our ground reaction force. But let's say we have a box on a horizontal surface on just a ledge right here. Okay, and the box on the table, the horizontal force must be greater than the frictional force for movement to occur. So let's say we just have this box, it's just resting on this ledge right here. There's no applied force, so all we have is the weight of the box and our ground reaction force. okay? But no actual movement is occurring in either the right or left directions. So let's say we're pushing the box. We still have the weight of the box and our ground reaction force. But when we apply a little bit of force, we have friction in the opposite direction here. Okay, so with no applied force, we have no friction force, and we have no movement. But when we apply just a small amount of force, we have a very small friction force. If the applied force is equal to the frictional force, there is no motion, okay, because our sum of forces is equal to 0. Okay, if our sum of forces is equal to 0, there is no motion. Okay, if the sum of forces is greater than 0, we see forward motion. If it's less than 0, we get into the negatives. If we're looking at two separate bodies moving, it'll move in the opposite direction. Okay, so let's continue on. So let's look if there's a larger applied force. So now we'll say that the applied force is now greater than the frictional force. So if we see that, that's where we start seeing motion occur. So let's talk about friction. Friction acts is a force. We measure it in newtons and acts at the interface of surfaces in contact. So once again, we'll have this ledge, box on the ledge. In between the box on the ledges, that's our interface, okay? That's where friction is acting, okay? It acts in the direction opposite to the motion occurring, or it impedes motion. There is both static and kinetic friction, and we'll look at those in just a bit. Static friction occurs when an object is static. So essentially, there is no motion. When applied, okay, when the applied force magnitude increases, then the static friction magnitude increases as a result. If static friction magnitude continues to increase to a certain point, we consider it to have maximum static friction. If the applied force increases beyond that point, that's where we start seeing motion occur. So static friction acts much like, we were talking about inertia, is the applied force has to be greater than the magnitude of the static friction for motion to occur. If we're looking at kinetic friction, we're looking at friction present during motion. This remains constant regardless of the applied force. It is always less than the value of maximum static friction. So let's look at how we calculate friction. What factors determine the amount of force needed to move an object? First, we have mu right here, if you're wondering how that's spelled, mu, mu. Mu is the coefficient of friction. It is unitless, okay? Coefficients, ratios are generally unitless. And then we have R for the normal perpendicular force. Therefore, to change the amount of force required to move an object, you can either alter mu or R, or both. So let's continue on. This is our normal perpendicular reaction force. Let's continue on. So once again, we'll look at static and kinetic friction. They are calculated simply the same. We're just using different coefficients of friction. The coefficient of static friction, let's say between a sled and some snow, is around 0.18, with a coefficient of kinetic friction around 0.15. So let's say a 250 Newton boy sits on a 200 Newton sled. How much horizontal force is required to start the sled in motion? How much force is required to keep the sled moving. Let's look at these. So let's look at static friction first. We'll look at the amount of force needed to start the sled moving. We have our coefficient of friction for static friction and our coefficient for friction for kinetic friction. Our normal perpendicular force is 250 newtons plus 200 newtons. The boy weighs 200 newtons, the sled weighs 200 newtons, and so we have a weight of negative 255 minus 200, so that'll give us approximately 450 newtons. So if we have a coefficient of friction of 0.18, multiply that by 450 newtons. Because this is unitless, to start the sled, we need a horizontal force of 81 newtons. Now to keep the sled moving, we'd simply, once again, we start looking at the same equation, but we're using the kinetic friction coefficient. And our regular perpendicular force is still 450 newtons. So when we multiply 0.15 times 450 newtons, once again, this is unitless right here. So we keep the newtons. So we need 675 newtons to keep the sled moving. Often this force would be provided by gravity. And then that force would be determined by kind of the angle of the hill this kid's on. Generally, the steeper the hill, the more effective gravity there is. The shallower the hill, the less effective gravity. So to start the sled in motion, we need greater than 81 newtons of horizontal force. To keep the sled in motion, we need at least 67.5 newtons of horizontal force. Hope this is making sense. Now let's talk about linear momentum. We already kind of talked about momentum in the intro to kinetics, but we know that momentum is simply the quality and how much quality of motion an object possesses. More specifically, it's the product of the object's mass and its velocity. Okay, it's the quantity of motion that an object possesses, and it's the product of the object's mass and its velocity. Its units are kilograms times meters per second times meters per second. Okay, because mass is our kilograms, velocity meters per second. So you'll see it written out like this. Or you might see it written out. Like this. Okay, let's continue. A 50 kilogram object is moving at 20 meters per second. What is its momentum? Well, we know that momentum is equal to mass times velocity, kilograms meters per second. So we have 50 times 20. So that's going to be roughly, we know that 2 times 50 is 100, but there's 0 here. So we're going to have roughly 1,000, right? Yep, 1,000 kilograms meters per second. Okay. What about a 1,000 kilogram object that is not moving? What is its momentum? Well, once again, L equals m times v. We don't even have to do the math because we know that velocity is equal to 0. Anything times 0 is also 0. So we're going to have a momentum of 0 kilograms meters per second. Okay. A change in momentum is either caused by a change in mass or a change in velocity. Okay. Our change in momentum is called an impulse. So following collision, there's a tendency for both the object to continue moving in the direction of the motion originally possessed by the object with the greater momentum. So basically, if we're looking at two objects colliding with each other, the resultant motion is going to be, let's say this has L right here for momentum. This has greater momentum. So we'll see motion with this one. Okay, it has greater momentum. So let's look at an example here. We have two hockey players. One has a mass of 90 kilograms, and they're traveling at 6 meters per second in the right direction, so it's going to be positive. Okay. The second hockey player has a mass of 80 kilograms and is traveling at 7 meters per second to the left, so it's going to be negative. They're heading in the negative direction. Which direction will they continue to travel after they collide? So let's look at this again. We have two hockey players. The first hockey player weighs 90 kilograms and is traveling at 6 meters per second. So they're going to have and remember they're traveling towards the right, so it's going to be positive. So they have a momentum of 540 kilogram meters per second. The second hockey player was traveling to the left, so it's going to be negative. Okay, and so we use the velocity with negative 7 meters per second. This is kilograms. So they have a momentum of negative 560 kilograms per meter second. Therefore, they'll travel in the direction of player 2 to the left with roughly a resultant momentum of negative 20 kilograms meters per second. Simply 540 minus 560 can equal negative 20 kilograms per meter second. Kilograms meters per second. Okay. So what we consider to be a change in momentum is an impulse. We already kind of talked about that. But an impulse is the product of force over time, the area under the force-time curve. With linear impulse, we simply say it's force times time. Okay? Once again, this little symbol is a symbol for integrals. That's what we use in calculus, which is so much fun. I hope, you might not use it much in your day-to-day life, but as you progress through your courses and you start working or you're planning on going to any sort of grad school, knowing how to use calculus will help you oh so very much in the future. So I really hope that you at least try to pick up some calculus in the future. But for our purposes, impulse is force multiplied by time. So let's look at our force-time curve characteristics again. We already did this in the last lecture. But let's say we apply 20 newtons of horizontal force to an object from 2 seconds to 3 seconds. So this right here is our 20 newtons of force. And we see nothing. Okay, there has been no impulse in the f of y direction. So we're simply applying that horizontal force. Okay, we're applying our f of x. So we're going to see no impulse in the vertical direction, but we will see an impulse in our horizontal direction. So our impulse is the area underneath this curve. Okay, if we applied 20 newtons for 2 to 3 seconds for 1 second, we're going to have an impulse of 20 newtons. Now let's say we're applying 20 newtons of force at a 30-degree angle to an object for 1 second. Well, to calculate f of y, once again we're using our sine trig function. So sine of 30 equals f of y divided by 20. So we'll have an f of y of 10 newtons. If we're looking at our f of x, our horizontal component, we use cosine, right? So that would give us 17.3 newtons. These are our kind of drew some vectors in our free body diagram. So we'll see this table will be moved upwards by about 10 newtons with a force of 10 newtons. And it'll be moved forward with an impulse of roughly 17.3 newtons. Now this kind of gets into, if we wanted to move a table, would be better to push or pull it. If you did the same thing but you were pulling it, you're going to lift it up a bit. By doing that, you're reducing the static friction required to get something to move because you're reducing the area it has a context to floor with. So this is why when we start looking at, if you were to look at, is it better to push or pull something? Pulling it might be better because you're going to be pulling it. And if you're pulling it and you're pulling it kind of upwards, you're reducing the contact surface of, let's say, this table on the ground. If you're doing that, you're reducing the area that static friction can be applied to. Hope this is making sense. Now let's look at the same thing, but we're going to increase the time to 2 seconds. So once again, we'll calculate our f of y using sine and our f of x using cosine. We'll draw a little free body diagram right here. And we're going to see is the force, the vertical force here doesn't increase in magnitude, but it has greater time. So we're looking at a greater impulse because there's more area under the curve. And we see the same thing with the horizontal component here. Okay, it still has the same magnitude, but that same magnitude is being applied for a longer time. So we're going to see more movement. So impulse is dependent on both the magnitude of the forces and on the length of time over which each force acts. Excuse me. Therefore, if a different force is applied for the same time duration, the impulse is different and a different movement occurs. If a force of the same magnitude is applied for different durations, the impulse is different and a different motion occurs. See, if we increase the time, we're seeing more area under the curve, so we're seeing a greater impulse. So we see a different motion. This kind of leads us to our ground reaction forces. Okay, let's draw the vertical components of these ground reaction forces. This is the first one right here. And as we go towards kind of our mid stance in our walking here, in our gait, our ground reaction force becomes more perpendicular to the ground because our foot is making a straighter angle towards the ground. So as we do this, the horizontal component here decreases all the way up until mid stance and then starts to increase again as we go into toe off. And we can use this to plot kind of the vector magnitude versus time for each direction. So f of y is always in a positive direction, especially when we're looking at somebody walking, assuming their foot's not going through the ground. So it's always positive, and there's 2 peaks with the dip in our mid stance. Okay, it's because we're seeing that right here this is where we usually see that our knee is beginning to flex when we start walking. So it's kind of complying with that ground reaction force. It's absorbing that force. So you see that dip. But here is our heel strike, and here is our toe off. Okay. With our f of x, there's initially a negative direction, and then a positive direction with 0 at mid stance. Right here is our heel strike, and if we're applying this vector towards the ground is complying and pushing back on us. So we'll have negative here, and this is our mid stance, where that f of x is now 0, because essentially if this is the ground, we're pushing completely perpendicular to the ground. It's pointing back up at us, but there's no forward motion. And then finally at toe off, right here, we're pushing against the ground like this, and the ground is pushing like this. So we're seeing greater force in the horizontal direction. So how do we calculate impulse? Remember, impulse is equal to force time multiplied by time. Impulse is also important during landing from jumps and catching a ball. So think of this. If a person locks their joints during these movements, let's say they're falling from a ledge, and they keep their legs as straight as they can, would their force at their feet and then their legs and their hips be greater than if they, when they started hitting the ground, they started going into flexion at their knees, at their hips, and then started going into a bit of dorsiflexion at their ankles and feet? Well, that's going to increase the time a force is being applied, so it's going to be less over time. A good way of looking at this is, let's look at skydivers, okay? Especially if you were looking at when they started using parachute troopers in the Army, is when they land, they don't land on their feet. Well, they land on their feet, but as soon as their feet touch the ground, they're taught to essentially crumple up and fall towards the ground, not land with their legs extended, because they're still moving at like around 25 to 30 miles per hour with those parachutes. If they did that, they would dislocate their legs at their hip. They'd probably break their legs. So by kind of bending their knees and crumpling to the ground, they're increasing that force over time. So they're seeing a lower impulse of force. So it's a little bit safer. Another good example of this is if we look at baseball and cricket. If you don't know what cricket is, it's like baseball, it's a little bit different and takes forever to play. The big difference is in baseball, players use baseball mitts. They have nice webbing in it, kind of saves their hand a bit. In cricket, it's a little bit smaller, but it's a very dense, hard rubber ball, and they don't really use mitts. So when somebody is trying to catch a cricket ball, what they'll do is they'll move their hands with the ball before they begin to touch it and catch it. Therefore, it's increasing that time period in which the force is being applied to their hands, so it makes it so they don't break their hands when they're trying to catch a cricket ball. So basically, what can a person do to reduce the impact force? Best way to do it, increase the time applied. When an impulse acts on a system, the result is a change in the system's total momentum. Remember that momentum is the quantity of motion. The altered impulse will alter the momentum, the amount of movement, for example, the height of a jump, the distance of a jump, the velocity of the movement, and the amount of impulse generated by the human body can be intentionally manipulated. Once again, we're increasing the amount of time this impulse is generated over. So if we wanted to say we're going to look at sprinters, okay? This first one, we're showing sprinters horizontal impulse from using starting blocks, okay? This results in faster starts than starts by conventional coaching techniques if they're just plantar flexing against the ground. Now, if we use a starter block like this, and they're placing their feet like this, we see that the magnitude of the impulse is the same. These peaks are generally the same, but it's applied over greater time, okay? But the longer the force is applied, we see greater velocity. So this actually makes them faster off the blocks. So now let's talk about impact. Collision is characterized by the exchange of a large force during a small time interval. So this is like a football tackle, okay? The behavior of the two colliding objects is dependent upon their collective momentum, and the nature of the impact, whether it's elastic or plastic. Okay, when we say elastic, a perfectly elastic impact is an impact during which the velocity of the system is conserved. Okay, so if we're saying we have like a bouncy super ball, if we throw it against the ground and it's traveling 100 meters per second, just to keep it simple, as soon as it hits the ground and bounces, it's still traveling at 100 meters per second. Its velocity is conserved. Okay, it approaches perfect elasticity. If we're looking at the opposite of something being perfectly plastic, this is an impact resulting in the loss of a system's velocity. So at least one of the bodies is deformed and does not regain its original shape. If we're looking at, you had some modeling clay and you threw it against the ground once again at 100 meters per second, and it's perfectly elastic, as soon as it hits the ground, it stops moving. It's no longer has any velocity whatsoever. And if you had it in a ball and you threw it against the ground, it flattens against the ground. So there is a spectrum of impacts ranging between perfectly plastic and perfectly elastic impacts. So when we look at this, that's where we start talking about the coefficient of restitution. It is the index of elasticity for colliding bodies. It is a unitless number between 0 and 1, with an elastic impact being a perfectly elastic impact equaling 1 and a perfectly plastic impact equaling 0. This governs the relationship between the relative velocities of the two bodies before and after an impact, with a negative being relative velocity after the impact and relative velocity before the impact. Now let's talk about work, power, and energy. Work refers to mechanical work. We could talk about chemical work. This is the work of your metabolism. But for biomechanics for this class, we're looking at mechanical work. Okay? Work is the force multiplied by the displacement of the resistance in the direction of the force. We use joules. Okay? Work is simply force multiplied by displacement, or it can be considered the change in displacement. Another good way of looking at this is since force equals mass times acceleration, work would equal mass times acceleration times the change in displacement. So work equals mad. Okay? Mass times acceleration times the change in displacement measured in joules. Okay? When a force is applied to a body but no movement results, what is the work? Well, no movement results. There's no displacement. If you multiply anything by 0, you get a product of 0. So there is 0 work, 0 joules. What type of contraction has 0 work? Well, we have our 3 types of contraction. We have a concentric contraction, an eccentric contraction, and an isometric contraction. In a concentric contraction, the muscle moves towards its center. In an eccentric contraction, the muscle moves away from its center. So in an isometric contraction, remember iso means same, metric means length. There's no change in length in an isometric contraction. So there's 0 displacement. So in an isometric contraction, there is 0 work being performed. It is important to remember it's 0 mechanical work. Your body is still using calories, which is it's a measure of energy. So it's still doing chemical work to make sure the muscle's still activated, but there's 0 mechanical work. So when a force is applied to a body but there's no movement, there's 0 work. And an isometric contraction is a contraction that has 0 work. So muscles produce force, the segment then moves, and the muscle has performed work on that segment. For positive work, we're looking at a concentric contraction. Negative work is an eccentric contraction. Positive work requires an increase in caloric expenditure, okay, compared to negative work. So you can think that increased work equals increased caloric expenditure. However, a simple relationship between mechanical work and caloric expenditure simply does not exist. We can look at work, it's in joules, and caloric expenditure is in kilocalories. And there's even a conversion from joules to kilocalories. But if we're looking at, if you wanted to see, how many kilocalories you use to climb up a flight of stairs, we can calculate and predict the mechanical work necessary to do this, and then convert the mechanical work to kilocalories and say at least this many kilocalories are needed to produce this, but we don't know exactly how many are actually used. That's dependent on a lot of factors. We start going in chemistry and physiology as far as the muscle's metabolism, when we look at, well, is somebody breathing heavier when they do this for somebody else? So there's too many factors to have a simple relationship between mechanical work and the actual caloric expenditure. So a good example of this is an isometric contraction. Once again, zero mechanical work is being done in an isometric contraction, but kilocalories are still being used to perform this type of contraction. Now let's look at power. This is the rate of work production, okay? We call it watts, okay? The imperial unit of this is horsepower, okay? Watts is by the Scottish physicist, I think Edmund Watts. I always forget his first name. His last name was Watts. He came up with this. We use his last name. Power is the rate of work. So it's work over time. Work is force times distance. So let's look at this again. If work is force times distance and force equals mass times acceleration, work is MAD, mad. So power is work mad over change in time. So it's almost how quickly does something get mad? Okay, you need a mnemonic to memorize this stuff. So power is force times displacement over time, and velocity is displacement over time. So there is kind of a continuum here where all we're really doing is power is dependent on the velocity of something. So power is force times velocity. Therefore, power can be expressed in either way. I like just saying power is equal to this. I think this is it's easy to look at this, but if you're not given, these in a question, but you're given velocity, if you multiply velocity times the applied force, you can get power as well. Okay, so let's look at the ability to produce mechanical power. The ability to produce mechanical power is critically important when we look at athletes completing in explosive types of events. In track and field events, when we look at the shot put, jumping, sprinting, if we're looking at American football with the linemen, they have to basically go from an almost kneeling stance to upright extremely quickly and apply force against the defensive line that's trying to tackle the quarterback. So the ability to produce mechanical power quickly is very important in athletics. But let's take a look at somebody going upstairs, just for the heck of it. This is a very simple example. It's a classical example that might be used in one of your homeworks. It might be used in an exam question. There's a very good chance of that. But let's say a 500 Newton person, so they weigh 500 Newtons, runs up a flight of 30 stairs, okay? Each stair is roughly 20 centimeters high, okay? In 10 seconds. What is the mechanical work and power in, let's say, the vertical plane, okay? So our y-axis, okay? There's also, we can look at it in the x-axis as well. And in fact, if we knew this as well, we can look at kind of more of a resultant work and resultant power, because depending on the inclination of the stairs, there's more or less work required. But we won't, while it's fun to do, you won't totally really be required to do all of this for a problem like this. So now let's solve this. Once again, we have a 500 Newton person running up a flight of 30 stairs that are each 20 centimeters high in 10 seconds. Let's solve for the mechanical work and power in just the vertical plane. So we know that work is force times distance, or once again, we could just say work equals mass times acceleration times displacement. And remember, for our acceleration, especially if we're doing vertical work, that's going to be, our acceleration is gravity, and gravity is always 9.81 meters per second squared. So before we do this, we know that we're using 500 newtons of force. This is equivalent to our weight. Let's solve for displacement first, because I gave it to you in centimeters. So we have 30 times 0.2 meters here, because there's 100 centimeters in a meter. So first we do this conversion. Their displacement is 6 meters. So we know that work is mass times acceleration times displacement, or force times displacement. So we have 500 newtons times 6 meters gives us 3,000 joules. And if we really, really wanted to, we convert joules to kilocalories and say this many kilocalories is required to go up these flights of stairs. But we don't know if that's actually the amount of kilocalories used. We just know that's the amount at least required. So now let's solve for power. Remember that power is work over time, or mad over time. So we don't, if the question just asked you for power, you don't really have to solve all this stuff. Solve just for work, and then just put work here and divide it by time. Okay, so power equals work over time. Our time is 10 seconds. So power, we had 3,000 joules divided by 10 seconds. It should say joules here. I can't spell. And this is seconds here. So 3,000 joules divided by 10 seconds is 300 watts. Be important, especially when you're doing your homework and like that you're labeling everything correctly. A lot of times you can shorten watts to just W. Now let's look at energy. Energy is the capacity to do work. So no work is done, no mechanical energy is used to do that zero mechanical work. We measure it in joules. Okay? Remember is when we're looking at work and energy, we're only talking about mechanical work and mechanical power. We're not looking at chemical energy either. So there's two forms of energy that we'll talk about here, kinetic and potential energy. There is a third type of energy that we will touch on, and that's strain energy. Strain energy is the energy of deformation or deformation, okay? It's very similar to kinetic energy. We're simply looking at how much energy is gained or lost when a body deforms. But we'll look at that in a bit. It is important to, especially if you've taken like year 1 physics, that you understand the continuation or conservation of energy principle. And we'll talk a little bit about that when we talk about equilibrium. But essentially, you might have seen this before, but C, basically total energy equals kinetic energy plus potential energy plus strain energy. And C, all of that is equal to 0. Okay? This allows us to kind of look at this in general, and we'll talk about it more when we start talking about equilibrium, that when one of these values change, the other one changes as well, so that the total energy within the system remains constant. You can't create or destroy energy. So we're saying C is a constant of energy. It's always equal to 0. So when kinetic energy changes, so does potential and or strain energy change. Okay, it's just kind of good to keep that in the back of your mind. So let's look at kinetic energy first. Kinetic energy is the energy of motion. It is equal to 1/2 of the mass of an object times its velocity squared. This is important that you remember how to calculate this, okay? Remember your orders of operation. First, you use half of the mass, then you multiply that half of the mass by its velocity squared, okay? So if you're calculating this, don't calculate mass times velocity squared and then take half of that. Don't do that. First, you calculate half of the mass, then you multiply it by its velocity squared. So note a body possesses kinetic energy only when in motion. If velocity is 0, then kinetic energy is 0. So let's look at two examples. A 2-kilogram ball is rolling with a velocity of 1 meters per second. What is its kinetic energy? Well, half of 2 kilograms is 1 kilogram, and velocity squared, 1 times 1 is 1. So 1 kilogram times 1 meters per second gives us 1 joule. Okay? Let's look at this other one. A 2-kilogram ball is moving with a velocity of 2 meters per second. Half of 2 kilograms is 1 kilogram. 2 meters per second squared is 4. So 1 kilogram times 4 meters per second is 4 joules. Hope this is making sense. Now let's look at potential energy. Potential energy is the energy of position, and it can be thought of as stored energy. Essentially, the higher something off the ground it is, the more potential energy it has. Just like in kinetic energy, the faster or the more mass an object has, the greater kinetic energy it has. Potential energy, the greater it is off the ground, or the more massive it is, the more potential energy it has. So potential energy is equal to mass times gravity. Remember, gravity, the acceleration of gravity is equal to 9.81 meters per second squared. And h is a body's height above a reference, usually the ground or floor. And once again, gravity is acceleration due to gravity. So let's look at another example. We have a 10-kilogram bar is 1 meter above the ground. What is its potential energy? So we have mass equal to 10 kilograms. Gravity, the acceleration due to gravity is 9.81 meters per second squared. And height equals 1 meter. So we just take 10 times 9.81 times 1. So it doesn't really matter too much, but we'll do it anyways. That's going to give us 98.1 joules. What is its kinetic energy? Well, we know kinetic energy is equal to 1/2 an object's mass times its velocity squared. In this question, we said nothing about its velocity. So we assume its velocity is equal to 0 meters per second. So anything times 0, even if you square 0, it's still going to be 0. So its kinetic energy is equal to 0 joules. Okay, I hope this makes sense. Let's keep going on. We'll talk about strain energy. Next, let's look at strain energy. Strain energy is kind of a special form of potential energy, where it's equal to 1/2 of a spring constant times the distance it's been deformed squared. This is, if you've taken year 1 physics, you've heard of Hooke's law. So Hooke's law. And basically that kind of states if you take an object and you deform it, you're storing energy within that object. And then when it goes back to its original shape, it releases that energy. So in, once again, first year physics, the kind of, common example or lab you do is you take a spring and you stretch it out. And as you stretch it out, you're storing strain energy into it. And as soon as that spring is released, it releases that strain energy. And much like the kinetic energy equation, it's important to follow the order of operations here. So first, you take 1/2 of the spring constant, and then you multiply it by the distance of deformation squared. Okay, so it's important to look at this. So first, 1/2 of k times the distance of deformation squared. So it's important to remember these orders of operation. So when an object is stretched, bent, or otherwise deformed, it stores strain energy for later use. When the object returns to its original shape, kinetic energy is released. So an example of this is muscles. Remember that stretch shortening cycle? That's where we start looking at the use of strain energy. Okay, first you stretch the muscle with an eccentric contraction. You're storing strain energy into that muscle. And then if we're looking at, the tendons of the muscle as well, you're storing strain energy into them. And then when you do that concentric contraction, you're converting that strain energy into additional kinetic energy of the muscle shortening. Okay. Once again, think of the baseball player or the baseball pitcher leaning back to start his pitch. He's storing that strain energy, and then when he goes into the forward motion of delivering his pitch, that strain energy is then converted into kinetic energy and added to the kinetic energy being created by the forward movement of his arm. Other examples, a diving board, trampoline, pole vaulting. When you jump on a trampoline, when you land, you're storing that trampoline is kind of being stretched beneath you. You're storing strain energy of that trampoline. And then when it starts bouncing back, it's converting that strain energy into kinetic energy to basically push you back up off of the trampoline. So let's talk about that conservation of mechanical energy. Remember when I wrote this, that C is is basically all of the energy, and it's equal to kinetic energy plus potential energy plus strain energy, and it's equal to 0. So when one of these changes, the other has to change so that energy remains constant. If we're looking at a ball tossed up in the air, we can start looking at potential and kinetic energy. The ball hasn't been deformed, so we don't have to consider strain energy here. But if the ball were to fall and hit the ground, the ball might deform, the ground might deform, so that's where strain energy might be used. But for right now, we won't consider strain energy. So as the ball gains height, you've thrown this ball in the air, as it gains height, it's gaining potential energy, but it's losing kinetic energy because as you're throwing it up, as soon as you release the ball, it's at maximum velocity. But the higher it goes, it starts losing velocity. So you start losing kinetic energy. At the apex, so right here, divide this into thirds. This is where you're increasing potential energy, but decreasing kinetic energy. At the very apex, let's find a good, right here, at the apex of the trajectory, you have maximum potential energy, but zero kinetic energy. So potential energy is at max, and kinetic energy is at zero. This is because at this point right here, it is the ball is at the highest it will be, but at that very point, at the height of its trajectory, it stops moving, if only for a thousandth or hundredth of a second. My tongue didn't want to cooperate with me there. Thousandths of a second or hundredths of a second, split second. At that very point, it stops moving. So if its velocity is zero, kinetic energy is zero. Then it begins to fall, and we'll say this third right here. And during this third, it's losing height. So we're going to see a decrease in potential energy. But as it's falling, it is building velocity. Its velocity is increasing. So we're going to see an increase in kinetic energy. Okay? So as a ball loses its height, we're assuming if it's losing its height, potential energy is mass times gravity times its height. If height is being lowered, then potential energy is being lowered. But as it's falling, it's starting to build velocity. So it's going closer towards its maximal kinetic energy. Obviously, if a ball falls and falls and falls and falls, everything reaches a terminal velocity. So, it's going to level out eventually. But as a ball falls, it's losing potential energy and gaining kinetic energy. And then if it were to hit, the ground, the grass, after it's rained a lot, perhaps, as the ball hits the ground, it's going to, maybe it'll bounce a bit, or it'll kind of sink into the ground. That's where we start seeing potential energy reaches zero, and then it stops, so kinetic energy is zero. But it's released that strain energy into the ground, so now the ground is deformed. If the ball bounced a bit, it used strain energy to create a bit of elastic energy. But as it settles, they all go back to zero. Hope this is making sense. So examples of the work energy in the human body. In running, we've seen in research that the arches in the feet and the Achilles tendon act to store and return strain energy to the foot. This is called one of these concepts is called the windlass mechanism. And basically we see deformation of the arch in the foot to store that strain energy. It's a kind of a cool, neat concept that if you have time, I suggest you look up. It's called the windlass mechanism. Windlass mechanism it's from sailing. The windlass mechanism is simply the mechanism that's used to tighten the sails on a sailboat so that they're more responsive to the wind. But essentially, when we're looking at, kind of the arches of the feet and the Achilles tendon, this can be used to reduce the total mechanical energy required by the muscles by about half. So it makes kind of our foot and ankle much, much more efficient for running. So this is the end of this lecture. I hope that it was helpful. And as always, if you have any questions, please feel free to contact me. Office hours are from 8 to 10 a.m. on Friday mornings. If you prefer to have your question answered before then, you can reach out to me through email and I can answer your question through email, or we can do a private Zoom meeting as well. Hope this helped, and goodbye.